record button. Again, after this class, you're not going to be able to go out necessarily and put up formwork and lay reinforcement, but at least you need to be conversant with what the drawings say and what the reality is that those drawings represent. Again, as I've said a number of times, construction documents, construction drawings exist in 2 dimensions, and it takes the skill of a contractor and tradespeople to turn that 2-dimensional drawing into 3-dimensional reality, right? Into a 3-dimensional building that stands up and supports the loads that it's intended to support. And it's the skills of the architect that represent that on a 2-dimensional drawing. So each of us has a role to play in the construction business. Again, my intention here is to collect up a bunch of information on green building and go through that toward the end of the semester. So again, certainly one of the things we learn about that I'll try to cover later on, and certainly that I cover in more detail in ARC 110, is how to minimize the amount of waste that's produced in the process of building a building. Okay, and so again, I am on Unit 11. This is starting on page 189 in the textbook. Generally speaking, commercial and industrial buildings are built with a structural framework of either reinforced concrete or structural steel, right? Concrete or steel. A small commercial building might be built out of wood, but there's obviously a limit to the size of what we can do with a wooden building. So, a small multifamily apartment building might be built out of wood or a combination of wood and concrete block, but anything larger than that is going to have a structure of either concrete or steel or some combination. Right? We can produce a concrete structure by a number of different methods. Cast in place concrete means it is done on the job site. The forms are constructed on the job site. The reinforcement is placed, the rebar is placed at the job site by tradesmen. And the quality of that construction is obviously impacted by the conditions in the field. Hot, cold, wet weather, late Friday afternoon, all the things that can impact the quality of how contractors and tradespeople execute their jobs. We also have the option of casting concrete off-site at a plant called precast concrete. Obviously, in a controlled environment in a factory, we can take out a lot of the impacts of weather, but we obviously need to make that, there's a limit to how big the piece can be because it has to get put on the back of a truck and transported to the job site. Good example of precast concrete construction. If any of you have driven around near Triton in the last 6 months or so, maybe the last year, you've noticed that Amazon has put up a bunch of warehouses and distribution facilities just south of Triton at Fifth Avenue and North. And if you look carefully, you'll see that was done, or if you remember how it was put together, that was done with precast concrete panels. If any of you saw that under construction, you might have seen something like figure 1117 on page 196, right? A large crane lifting panels off the back of the truck and erecting them. So again, precast concrete is limited by how big the piece can be that gets put on the back of a truck. And obviously we can use concrete as an architectural element, right? We can treat it in various ways to create a finished surface. Number of different types of concrete floor systems. And again, I am on page 190 in the textbook. Right, a one-way slab system, right? The reinforcing steel is going to span in one direction with the members running parallel to each other, right? This is very similar to what we would do if we were building in wood, right? We have wood joists parallel to each other, spanning in one direction, and those joists might be bearing on a foundation wall or an intermediate beam, right? That would be the floor system that we have in Sullivan or Marseille, right? That would be the first floor of either of those two structures. We can have a two-way slab system where we have reinforcing steel running in two different directions. Or we can have a waffle slab system, and you'll see pictures of this in a minute. Again, this is reinforcing steel running in two directions. Right? In all these cases, the concrete is reinforced with steel, with rebar. Right? I've said it a number of times. Concrete construction is typically a combination of concrete and reinforcement. Right? Concrete provides the compressive strength, and the steel provides the tensile and the shear strength. It's a combination of those two things that provides the characteristics that we're looking for. Right, here's an example, a picture of a one-way slab system. And I always have to look carefully at this drawing because depending on how I look at it, sometimes it appears differently. But again, you see concrete beams bearing on a girder, which ultimately bears on a column. Again, very similar to what a residential wood framing system would look like. Yes, did somebody raise their hand?
Yeah, that was me. So in regards to the steel spanning in this diagram, which part exactly is the steel spanning? Because I'm really trying to understand the difference between the one-way slab and the two-way slab.
Yeah, no, good question. Yeah, in this case, we're going to have reinforcement running through each of those pieces of concrete, right? Concrete is always a combination of concrete and reinforcement. In this case, I think they're calling it a one-way slab because these beams are running one way parallel to each other, but ultimately they do have to bear on some other structural member, right? They're bearing on this girder or larger member, which bears on a column. So in a way that there's reinforcing running in two directions, but they're calling this a one-way slab system because the major structure are those beams running in one direction.
So when you when I'm looking at the diagram and also the picture, we're using the term beam and girder, but we're really talking about concrete members, right? The steel that we keep referring to is actually not in view right now when we look at those pictures. It's inside the concrete, correct?
Yes, that is correct. Yeah, you're looking at a picture of concrete or a diagram of concrete, but there will be reinforcing steel, inside that concrete, as part of the structure. So again, it's a combination of concrete and reinforcing steel that provides the properties that we're looking for. Yeah, again, conceptually, this could be wood, right? We could have We could have 2x6s, right? The beams could be 2x6s or 2x10s, bearing on a concrete foundation wall, or they could be, bearing on a steel I-beam, right? Again, I think we have an I-beam running down the middle of the basement in both Sullivan. Certainly, I remember seeing that. Or this could be done in steel, right? It's conceptually very similar, whether we're doing it in wood or concrete and rebar or steel, right? We have loads being transferred from one member to another and ultimately being transferred to a column, and that column ultimately bearing on, on soil someplace. Does that make sense?
Yeah, so we use some of these terms depending on which type. We could use these terms with talking about wood or steel or concrete.
Yes, that's correct. The
Okay.
term beam can apply to any of those materials. The column can apply to any of those materials. Yeah, we don't have a separate set of terminology for different, for different materials. We're using the same set of terminology and then applying it to different materials.
Got it. Thank you.
Oh, you're very welcome. Right, here is a two-way slab system. Again, lots of different ways that this can be executed, right? This is figure 11-4 on page 191 of the textbook. Again, we have a slab of steel, a slab of concrete with steel reinforcement, bearing on a column. In some cases, we might have a drop or a column capital or both, kind of helping to transfer that load from the slab to the column, kind of gathering up that load and making sure that load is transferred to the column. Here is a waffle slab system. Again, this is a variation on a two-way slab system. Good question. No, the drop panel would be concrete. Again, I'll see if we have any details here, Vaughn. No, again, this is all going to be concrete with steel reinforcement. So this would not be, the drop panel would not be a steel plate. It's likely to be a couple inches of concrete with heavier reinforcement than what we might have in the slab proper. Yep, again, we're trying to gather up that load and transfer that load to the column, right? The load might be in the middle of the floor here someplace, right? If this is there's a parking deck or an industrial building, right? We could have a load in the middle of that slab, and that load has to get transferred over to the column. You see a lot of cases where this is done, where this waffle slab system will be exposed inside the building, right? This is a good picture of it here, where you might have lights or other things kind of inside the waffles. Right, we talked about rebar early on this in the semester, where we're looking at materials. Right, so all these different things we just looked at, all the beams and girders and columns are going to be a combination of concrete and reinforcing steel. We have a number of different types of rebar and sizes, plain or deformed. Deformed, has the ribs on it. That's going to improve the bond between the rebar and the concrete. And again, the rebar is working in, the steel is working in combination with the concrete to resist all the various types of forces. Right, I had to stick this one in here. We saw the same thing a couple of weeks ago, right? Compression is squeezing something together. That's what concrete is good at. Tension is stretching something apart. Concrete is not good at that. Steel is shear, a sideways or lateral force. Again, concrete is not going to do well in shear, but the combination of concrete and rebar will perform well, right? Let's think about a couple of weeks ago, we were looking at the wall detail for Delhi, right? Remember we had that single 17-foot tall concrete block wall. I think it's on one side of, I forgot, I should have the drawings in front of me, right? But we had concrete block with reinforcing with number 4 rebar, I think either at 40 or 48 inches on center, right? We have that rebar in that concrete block to provide shear strength for that wall, right? Otherwise, that tall, thin concrete wall is going to topple over. But the combination of concrete block and reinforcement and grout provides the characteristics that we're looking for. So again, here's some pictures. This would be cast in place concrete, cast in place reinforced concrete. So a combination of formwork and reinforcement, right? The formwork is what holds the concrete in place. The reinforcement is what provides that tensile and shear strength. And that reinforcement has to be placed in certain locations to give us the characteristics that we're looking for. Right, so skilled tradespeople will look at the drawings, interpret the drawings, and basically put that rebar together, right? Place it in the right place, wire it together with the necessary supports so the concrete can be poured. Right, on the drawings, we identify rebar by the number and size and spacing. So 2 number 5 at the bottom there, 2 number 5 at 19 foot at 2'6" OC. OC means on center. So again, number 5 bar is 5/8 of an inch. So we're going to have 19 feet of 5/8 bar placed on 2'6", 2.5 foot centers. I'm not that terribly familiar with this, but just like any other product, steel product, the type and grade of that product will be indicated on the rebar. So the drawings or specifications, depending on the strength that they're looking for, may call for a specific type of steel of a specific grade. Remember way back when we looked at those couple of YouTubes about how they make steel, right? Remember, steel is iron with other stuff thrown in to give it specific properties. So if we're looking for specific properties in the steel, that will be called out in our drawings and specifications in our construction documents. Yes, Christoph.
In your experience, is it common to actually see those exact letterings and numberings on the rebar in the field?
This was actually news to me, right? I'm a mechanical engineer, so I don't deal with rebar on a day-to-day basis. I have a bunch of pieces of rebar that I've collected over the years that I use in my garden to, hold things up when my tomatoes get so big. But I'm I'm frankly not used to seeing those marks on the rebar, so that's a new thing to me. I just thought that rebar was size and pattern of deformation and length. I didn't know that there was this other stuff going on, right? Things are always more complex than they are. I mean, if you were if you're a concrete contractor or a tradesman doing this kind of work, then you're going to be familiar with this stuff. Right, so again, the bar number indicates the number of eighths of an inch. How did they come up with that system? I don't know, but that's the system that's out there. Right, we see a lot of things, a lot of our drawings have number 4 rebar, right, half-inch diameter. So again, here is cast in place concrete. We see the formwork is in place, the rebar is in place, and now the concrete's being poured. And it's, somewhere there'll be a tradesman who's making sure that that concrete flows in all the places that it's intended to be and totally fills up the formwork. Right, again, we have a number of steel products that can be used for reinforcement. We just looked at rebar, right? Welded wire fabric or welded mesh are other materials that can be used to reinforce. In this case, we have things running in 2 directions, the fabric or the mesh. Indicated by spacing and size. And this is on, let's find it in the book here. Maybe not. Sorry, I think I took some of this stuff from our materials lecture. Not me, the person who had this class before me touched up some of these lectures. We at Triton, this class gets taught by a number of different instructors, so we all try to make the lectures a little better each time, so the person who teaches it next time has a more complete set of material. Right, here's our welded wire fabric.
Could you go back to the, oh, sorry.
Go ahead, Nicole.
Sorry to interrupt. Could you go back to the slide with the numbers on it? So the 1.4, is that like the diameter of the wire? Is that what that means?
Yes, it's an indication of the size of the wire. I don't know if it's 1.4 watts, right? I would actually have to look. I'll find that answer for you. And your questions are never an interruption, Nicole, right? We're here to learn together. So a question is never an interruption. You're looking for information, and I'm going to try to give it to you as best I can.
Okay, thank you so much.
Oh, you're very welcome. I would be, if you're pouring a basement floor slab, or a floor, or a slab on grade in residential construction, I would easily expect you to see something like this. And that welded wire fabric will be laid on something to make sure it's positioned correctly in the concrete, right? So it's not at the bottom. So there might be, you'll see that there are some other pieces of metal that help position this correctly. I will find out what those numbers mean, because I know we took this from something else. I think this is actually cribbed out of Unit 7, but while we're on break, I'll figure that out. Right, here's welded wire mesh. Again, this looks a lot like rebar that's welded together in two directions. Right, so again, here's our tradespeople waiting for the concrete to start rolling. So again, combination of formwork, reinforcement, and concrete. As you remember, concrete can have, a variety of properties, compressive strength, et cetera, depending on the characteristics of that mix. Right, so the columns in a structural system, they're the vertical members, right? The beams and girders are horizontal members. The vertical members are columns. They're designed to carry the load of the structure. Sometimes you'll hear the term live load and dead load, right? So the structure has to carry both its own weight, which is the dead load, and also the weight of whatever is inside the building. That's the live load, right? So the structure has to both hold itself up and also hold up whatever it is that's going to be placed on top of it, being it a hotel or an industrial building or a high rise or a parking garage. So again, oftentimes there will be a schedule of columns. The column will be notated with a mark on the drawing and a column schedule, and that column schedule will indicate the details of what's inside that column. Right, the column schedule will typically be tied to a plan. I think we'll see that when we roll up our sleeves and look at Delhi here in the second part of the lecture, right? So we typically will see the columns located in plan with a mark or a tag, and that mark or tag will be referenced back to a column schedule, and that column schedule will have the additional details. Again, the combination of things in plan and things in schedule. If we try to crowd all that information just in plan, that'd be too much information, right? So we do with a combination of marks, tags, marks or tags, and a schedule, just like we do with windows and doors, lots of other things. Right, here's an example of a column schedule. A column schedule is figure 9 on page 193 of the textbook, and also a picture of what that column might actually look like in reality. Right, we see vertical pieces of rebar tied together inside of concrete. Excuse me, my voice is giving out here. So, right, we said before the terminology of beams and girders and columns Similar terminology exists whether it's a concrete or wood or a steel structural system. Right, here's our beams. Beams run horizontally, and they're going to bear on something else, another beam or a girder or a column. They have reinforcement. Some of these terms are new to me. Stirrups and chairs, right? Those are particular elements of the reinforcement that's going to hold that reinforcement in its proper position. So when you pour the concrete, the rebar ends up where you want it to be, right? You see in this picture here, we have more rebar at the bottom, right? The bottom of the member is where there'll be more tensile forces, right? Because we're pushing down on that member, so it'll be in compression on the top and tension on the bottom. And this is a section kind of showing how a beam and a column would get tied together. Again, the reinforcing is there to help transfer the load in the beam to the column. So again, this would be the structural engineer's business to figure all that out and detail it. Right? The structural engineer is the part of the design team that's going to be responsible for designing these structural systems to hold the building up. The architect will say, hey, I need something that's going to bear this much weight, 150 pounds a square. That's my design live load. So Mr. or Ms. Structural Engineer, you figure it out and make it as economical as possible so we can deliver this structure on the budget that our client is looking for. Again, I think I believe I grabbed this out of Unit 7. Again, we have a variety of different supports that are used to hold the reinforcement in place. Right, the chairs or the bolsters. Right, they're going to sit on the formwork and make sure that that piece of rebar ends up at the elevation that the structural engineer wants it to be. The structural engineer doesn't want the rebar at the bottom of the beam. The structural engineer may want that rebar to be 3 or 4 inches from the bottom of the beam. So these other pieces will make sure that rebar ends up in the correct elevation. Right, again, just like everything else, we'll quite often have a beam schedule where we have marks or tags on the plan, and those marks or tags reference a schedule that gives additional detail. Right, so here's the size of the beam, the reinforcement at the top and the bottom, and stirrups are what's holding that reinforcement in place during the pour. And again, this is figure 11-13 in the text on page 195 of the textbook. Right, this looks like a floor slab with a beam or a girder. Right, this probably looks like a girder running here and another structural member running in this direction. Obviously, these guys are going to be, this intersection can be bearing on a column. So you see the various types of rebar that have been placed. From a trade's perspective, I think it's carpenters who lay the reinforcement in steel, but I don't know for sure. Here's an example of a framing plan. This is figure 11-14 in the book. Yeah, it's a little hard to see on the screen here, a little hard to see in the book as well. Probably very hard to see if you're looking at a virtual textbook rather than the physical one. But you see the column lines or grid line, that the indication of columns, right? So just like in a checkerboard, column line, column N3 or column lines N and 3 intersect. And you can see the beams and joists and columns that go into that structural system. Sometimes we have requirement for the length of reinforcing steel that exceeds the available length of rebar. I actually don't know how long pieces of rebar can be. I'm guessing probably somewhere 35 or 40 feet, right? Because it's got to fit on the back of a truck, and it's got to be something that can be lifted in place and handled reasonably well. But if for some reason we need reinforcement that exceeds that available length of rebar, then we have to lap that rebar together. So I believe that lapping is done with wire. I don't believe that we mechanically fasten or weld. I believe in most cases we're tying things together with wire. So again, a tradesperson, whatever trade is responsible for the reinforcement, it's their job to read the drawing, interpret what's required, and execute that in the field. Okay, so we have been talking about cast in place concrete. Remember, cast in place means that it's done in the field. The formwork is built in the field or erected in the field. The rebar is placed in the field. The concrete is poured in the field. And the quality of that work obviously depends on all the tradespeople and the concrete supplier and the ability to execute in the field. One way that we can control quality is by doing stuff in a factory in a controlled environment. Right, third bullet there says casting in a controlled environment produces a higher quality product. Right, just like we have the option of prefabricating wooden buildings in a controlled environment. So we can certainly build a building out of precast concrete if we so choose. But again, we are limited by how big of a piece of concrete and how heavy a piece of concrete we can transport to the job site. Again, this is a very common way that, right, if you, I mentioned the Amazon distribution center right near Triton. If you drive out the Stevenson, drive out I-55 out southwest to I-80, you see miles and miles and miles of these distribution buildings that have been put up in the last 15 or 20 years. Right, there are all these precast concrete panels, and you see these little guys here that are holding the panels up. Those will be there until they, put the roof structure in place, and the roof structure is what's going to hold the whole thing together. But again, it seems to be a very common technique for building warehouse buildings and distribution centers. Okay, so that's precast concrete. The other thing we can do with concrete is we can pre-stress that concrete. We can pull that lower half of the beam together before the load is placed on it to improve the structural characteristics. Right? Remember I said a few minutes ago that the top half of that beam is going to be in compression and the bottom half is going to be in tension. So if we add some additional force in the bottom half of that beam, we can improve the strength of that system. Right, so it says, go ahead.
Could you say that one more time? You said the top half has the tension and the bottom half?
Yeah, no, the opposite. Right, remember compression is squeezing something together, tension is pulling something apart. So just imagine that right, I have my pen in my hand, which you can't see, right? I'm pushing down, or you could do it with anything that you have at hand, right? If you push down on imagine that you're pushing down on something that represents a beam, right? The top of that beam is going to be in compression because it's being pushed down, and the bottom half of that beam is going to be in tension because it's being stretched out. So the forces are not uniform throughout the entire member. So the idea of pre-stressed concrete is that we want to use techniques to provide some additional tensile strength in the bottom half of that member to improve the structural characteristics of the entire system.
Thank you.
Right, so it says here pre-stressed members use less material. Right, I'm the architect. I just challenged my structural engineer to, hey, deliver a structural system that uses less material, because I want to be hero and have a structure with a low embodied energy. So Mr. or Ms. Structural engineer, got to help me out to achieve my goals, right? So the structural engineer may pull this out of their bag of tricks and say, okay, Mr. or Ms. Architect, here's my solution. Let's talk about it. Right, so we can either tension that concrete pre-tensioned or post-tensioned. Right, this is a lot of pre's and post, a little bit complicated terminology here, right? So again, we are pre-stressing the concrete. We're adding stresses to it before it gets put in service. So in pre-tensioning, right, we lay that cable out in tension because it's steel. I'm on the this is figure 1118 in the textbook on the bottom, and 1119 on page 197. Right, I put a cable in place. I put it in tension. I cast a beam around that, and then in pre-tension concrete, I cut that cable, and now I place the bottom of that concrete in tension. I can do the same thing with post-tension concrete. Right, I cast the concrete with a tube and a piece of cable in it, and then I subject that cable to tension. And again, I've Now the pictures kind of exaggerate the bending, but you can imagine now I put load on that concrete member. The load is going to act in opposition to the way that is bent, right? The load is going to act downward, and the pre-stressing of the bending is going to act is going to act in opposition to the load that's being placed. Now, the only problem with pre-stressed concrete, there's probably a number of problems, but you really want to be careful if you're the electrician or the plumber that's got to drill a hole in that concrete slab, to run their conduit or to run their drain lines. You better know where that post-tension, where that steel element is located, or else you'll have yourself a nasty surprise. Okay, it's a couple minutes before the top of the hour. Why don't we stop here and take, we'll go 10-minute break or so. So we'll get started again maybe 7 or 8 minutes after the hour, because my voice needs a little bit of rest here as well. Any questions?
Is the cable in addition to rebar that would be inside?
A good question. I am going to say no. I think that would be taking the place of the rebar.
Okay.
That is a great question, Patrick. I don't specifically know the answer. I'm just hazarding a guess.
Yeah, I just thought it would, once it bent, that it would bend the bars inside too, and that.
Yeah, I'm going to guess that the cable would be. Let's just assume that cables will be taking the place of the rebar.
Okay.
But again, I think the danger with pre-stressed concrete is that all the other trades on the job have to know where that cable is, in the concrete, or else, again, they're gonna have a nasty surprise if they hit that thing when they're, with a hole saw when they're trying to drill something. Great. Okay. Well, let's take a little break, and we will get back together again in 10 minutes or so. Thanks, everyone.